Okay, so welcome to my fourth lecture in this series. And today I will argue the representation power of spheres. Okay, it should be the building block and call its atoms for a new AI, and this AI should be explainable and reliable. It's very good. So first, let me remove this. First, let me recap what I've talked about in my last three lectures. My first lecture is to argue that current supervised deep learning cannot reach the rigor of syllogistic reasoning, no matter how much training data you use. Okay, there is a gap you cannot close. One reason is that the training data itself generates out of the distribution data itself. Okay, then the next lecture is about, it's to introduce a novel neural network, if we call it sphere neural network. The difference is to change the representation. We don't use vectors, we're using sphere. We blow these vectors into a sphere. Okay, and how they work. And my third lecture is to prove seriously that the sphere neural network reaches the rigor of symbolic level of syllogistic reasoning. This means if a reasoning is unsatisfiable, the network knows there's no model. How it comes? We prove for any unsatisfiable statement. So as long as there is a model, sphere neural network can construct this model in one epoch. We need to prove this one. So after the first epoch, the neural network fails to construct a model. With this proof, the network will stop iteration and says no model. The conclusion is unsatisfiable, so the negation of the conclusion is valid. Okay, and this proof is only valid for syllogistic reasoning. And today's lecture is how far can sphere network go? That's a natural question because we cannot only solve syllogistic reasoning. So today we'll talk about what is a sphere and what kind of knowledge we can use sphere to represent, and how we reason or solve tasks using sphere configuration. Okay. So first question is, what is a sphere? It's very easy question, right? This is a sphere. Sphere has a structure, it's a century, and has a radius. It's a sphere is a set of points, a set area. Any point, if it's the distance to the center is less than the radius, the constant value, then it forms a region as a sphere. That's our common sense understanding. But if we think a bit more, say, this is a circle, this is the sphere in a 2D Euclidean space, and that's a circle. What is a sphere in a 3-dimensional Euclidean space? It's a ball. Okay. That's also easy to understand. What is the sphere on the surface of the 3D sphere? Surface. Can you imagine? What's that?
Actually,
It's what?
it's a set of points that has a constant distance in the center.
Yes, but what's the shape of this sphere? Yeah.
That locally is Euclidean, but globally is a sphere.
Yeah. But it's on a 3D surface. So if you stand at the North Pole and draw a circle, what's that? It's not a circle, it's not flat, it's a curve. Yeah. So this is the curve. So see, sphere is also, this is really a transform, it's transform shapes if we define different universe. Circle to ball to curve. What if the universe is a line? The sphere is a single segment, right? I just say you crashed the 2D space into a line, and the sphere just into a segment. If the universe is the 2D circle, if this is the universe, and what is the sphere on this circle? Yes, great. And what is the power of this representation arc? The complement of a set is also an arc. It's closed. Yeah. And it's very useful. So it's an arc. Now, for any universe, what if the radius reduce to 0? Then the sphere, the cone, the segment, the arc will become smaller, 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 and become a vector. What does this mean? So cool. The first law of sphere neural network. Sphere neural network is a generalization of traditional neural network. Traditional network optimize vectors, a special kinds of sphere. Exists any operation, any method to optimize a vector can be applied to the center of sphere. So sphere neural network do not lose anything. Okay, if you have data, you can predict the center of the sphere. And sphere network has boundary. The traditional network don't have. Okay, this is the argument because any sphere has a central vector. And traditional neural network are the special sphere neural network where all radius are set to 0. So we established a relation between traditional neural network and sphere neural network. And why this is the and from this perspective, sphere is a natural object to realize neuro-symbolic unification. Let's see if we have vector embeddings to predict the center of sphere. And on the other hand, we have symbolic relation. Let's say it's a tree. And tree structure can be represented as nested spheres. In that case, we can create a sphere embeddings, a sphere configuration whose centers to preserve precisely pre-trained data from traditional neural network. And the boundary relation, the part-whole relation, to precisely encode tree structure, the child-parent relation. How to do this? Sometimes we need to create this in higher dimension, okay, because the training data has bias, and there's some problems if we create the tree sphere embedding in the same dimension as the pre-trained vectors. So in this example, we keep the pre-trained vector of Berlin and move it in another axis, shift Beijing's to some value to the left. Okay, and then we create a boundary to reflect the child-parent relation in the tree structure. Okay. Yes.
Just wondering how come you pick a sphere-like structure to represent something that is a tree-like structure? Because I thought that to represent tree-like structure, it's more suitable to use an hyperbolic space instead.
Yes, but we can also create this necessary sphere in Euclidean space. And this process is the construction process. We don't need data to train. And you also don't have this data because all data are trained to predict orientations. And this process, you just compute it. And then the second law of sphere neural network. Currently, the first law says mathematically, sphere neural network is the generalization. The second law says which one first. And here says sphere neural network should be the forerunner of vector-based traditional network. For what reason? Our question is, can you imagine at what age would you understand the concept of point? Middle school? Yes. At what age you understand concrete object, understand the ball, an apple, chairs? We understand concrete object first. So if we using neural network to simulate how our mind work in the stage before you go to middle school, there's no concept point. Then we should represent these concrete objects. Okay, we understand concrete objects before abstract one. So there should be some sphere neural network manipulate these concrete objects, represent, and then to solve problems. And then step by step, these evolve into to develop an abstract concept like point. The question is, how can we use sphere to represent concrete physical environment around you to simulate when you are a baby? Yeah. Okay, is it possible? And I want to show spheres are necessary and sufficient to represent common sense, spatial temporal knowledge without using these numbers, without measurement. So let's say what kind of knowledge are common sense spatial knowledge? So we are in this room, this topological relation. Okay, this iPhone is on this table, also connected on this table. And I'm in front of you. All these are common sense spatial descriptions. And this field is researched in the AI branch, this qualitative spatial representation and reasoning. There are three kind of common sense spatial knowledge: topological and distance and orientation. So first, to represent topological relation using spheres is quite straightforward. Actually, in the former lectures, I already showed this the 5 relation between spheres. The 2 spheres can be disconnected, partially overlapped. One is proper part of the other, or they are equal. Okay. Then, can we use sphere to describe distance comparison? How can we say the red sphere, the black sphere is nearer to the blue sphere than the red sphere without measurement? And the way is say, there is the 4th sphere that can connect with black sphere and blue sphere. And this green sphere cannot connect with black and red sphere, no matter how you move it. Okay, and this way the green sphere is nearer to the black sphere than the red one. Okay, so it use topological relations to define distance comparison. Connect. Green sphere cannot connect the black and red, no matter how you move it. And from this concept, we can define distance relation. If this green sphere has a unit, let's say meter, then we're using this step-by-step, say, we can say we're using minimum 3 such green sphere, one connected by another, then the black sphere can connect with red. If we're using 2, we cannot. This means the distance between black and red can be defined as 2 of the unit sphere, a point something. Okay. Then we can introduce in the concept of distance using the connectedness relation, topological relation. Now, orientation. How to explain I'm in front of you. There's no compass. I'm in front of probably means I'm in front of you. You are. I'm not in the backside of you means I'm closer to your front side than your backside. So a sphere has parts. One part has the named as front. Okay, the distance comparison between parts of the object. Okay, we need to check whether this is correct. This means orientation is kind of distance comparison. We checked first with dictionary. So left means something situated on the side of the body, which the heart is mostly located. So it means something closer to your heart. This means left. This kind of distance comparison to the location of heart. And if you look at the German dictionary, it's just a translation of this one. And this is the French definition. I don't know, you can check your language, Italian and Spanish. This is the basic definition of left. Is it compared with the location of your heart? Okay, now let's go to the mathematical definition. In geometry, what is the orientation of the point? The P in the 2-dimensional space. It can be represented by the formula A multiply the E with the power of minus E theta. as the complex form. A means the length of the vector OP, and what E with the power of minus I theta is the point on the unit circle. And this point Q is closest to P than any other point on this unit circle. Okay, we can prove this. Any point on this unit circle, the distance PR should be greater than the distance with PQ. So again, it's a distance comparison. The orientation of P is the point on this unit circle that is closest to P, the minimum value. Also distance comparison. Now we come to, then we need to define the distance between point to a region, to an area. We can have two kind of different definitions. One is say this area is settle point. The distance is the shortest distance. The other is that we choose the represented location of this point. Let's say the center of the area as the distance between the point to this region. Okay, the first is say the shortest. The second says we choose a representative location, say center, like did in physics. Use these two different distance definition, we can define a variety of qualitative orientation in the literature, all of it. So let's go one by one. Let's say the reference is a square, and then the definition is definition 1, means the distance between a point to the segment, the sides, is the shortest distance. This means points in this area between the two black segments, all points in this area is shortest to the red segment. Okay, and then using this method, it partitions this space into 8 areas. If the point in this between the angle of this black line, then it's the shortest to the 2 segment equal distance. This is the shortest distance to the 4 sides of this square. Okay, in this way, the space around this square is partitioned into 8 areas. If we name it into north, south, east, west, or something like that, it is the qualitative, one of the qualitative orientation defined by Andrew Frank in 1992. It's a distance comparison, okay, from a point to 4 sides of the square. If we replace the distance definition using the central point of the segment, okay, then point in this area is closest to the black segment. And the space is partitioned into 4 areas this way. We name it as, let's say, north, east, west, south. That's a different kind of qualitative orientation framework. The same Andrew Frank defined in the same book, same paper. And we switch to another one. If it's an octagon, and we're using the second distance definition, they partition the space into 8 areas. Andrew Frank defined it 1 year before, 91. If we replace this name using front, left, right, this way, just egocentric framework, as Hernandez defined in 94. This means we're using distance comparison, and we can enumerate all these qualitative orientation in the literature, even generate new one. Okay, this is another one. It uses the distance definition 1. Then it partitioned into front, the bit left, front left, and the flexor 99. If we replace these terms with north, south, west, and then let's say the size of this octagon shrink to 0, then the space is partitioned into another 8 area. This is another kind of qualitative orientation framework by Frank 91. Okay, if we summarize all of these orientations, orientation in everyday life, like front, right, all these kind, is a kind of distance comparison. If we type first, there is a shape of the reference object, and we define a distance comparison method. There are two different distance comparison methods, and we have a qualitative orientation framework. We can increase edges, increase sides, and we have a new one. In the end, if the number of edge go to the limit, then we have the orientation in geometry, the compass. So we prove that orientation in both everyday life and in geometry is a kind of distance comparison. So what difference is just we change the shape of reference object and change the method of distance comparison. Okay, and then all these form into a continuum. So this is 3 kind of so orientation. We just summarize it when the edge go to limit. So this means orientation from everyday life to mathematics, kind of distance comparison. So now we need to move on to use sphere to define temporal knowledge. Okay, we're starting from the 5 basic topological relation between spheres. And we introducing the array of time as a 1D with the orientation. And we project this sphere onto this 1D axis. And this sphere or this shape become a segment. Then add a direction of time. And we do the same. We can do all these things. This means temporal relation is a kind of spatial relation. On the time axis, and it's more specific because it's orientation. And in spatial relation, if 2 regions are disconnected, when it projected into the time axis, there are 4 kinds of temporal relation. So one is before the other, or inversely, or they just meet, or be met by. Okay. And overlap is also there's an order, which one is first. So it maps 2. And then proper part, there are 3. it determines whether the two ends are meet. Okay. And equal relation is just the equal relation. And then the 5 spatial relation is specified into 13 temporal relation. That is exactly the 13 temporal interval relation that described by Allen in 1983. Okay, we have a consistent representation using sphere in the embedding space. So now we have space and time. What's left is event. What is event? Actually, event is nothing new. According to the philosophy of Queen, event can be understood in the same way as we understand object. It has part-whole relation, and it has categorical relation. All right. Just like the understanding of table chairs, the difference is that it's bounded in space and time, so it's a dynamic. Event have category part. They can be understood normal object, but we need an example. What are event? How can we represent event using Cartesian product of sphere configuration? So let's start with the very part topological relation between San Diego and California. Reno is in Nevada, something like that. And they are geographical regions or object of the United States. Now we replace San Diego with doctors, also another city in maybe Los Angeles as this is a wife, and then California as the home of doctor and wife. Okay, and then Reno we replaced as a parent, Nevada and maybe a car. Then we have a street scenario that the patient is driving a car to visit a doctor. Okay, we can using the same sphere structure. Different is these spheres have different names. If this is a starting point, a snapshot view of an event, and we would understand this is the event of the patient to visit a doctor. Okay. So we will expect the outcome, the next step of this event is the patient will leave the car and inside move into the home of doctor. So event is the Cartesian product of sphere configuration with start and end of event. And sphere event has a clear target or goal. So, and it can move on dynamically. If the patient currently is outside the home and knock at the door and the pretty wife says the doctor is not at home. Okay. Then the event moves on. The doctor, what we would expect is the patient would be get back his car and drove away. Okay, that's expected end. So event is goal-driven. It is a causality relation support based on the temporal relation. But the pretty wife continue answered, come right in. And then we would understand that is a fear. What happens again? And this is a classic joke in the humor literature. Okay. The joke looked like this. Is the doctor at home? The patient asked in his bronchial whisper. No, the doctor's young pretty wife whispered in reply, come right in. Okay. And if you look at the representation, pairs of sphere configuration is enough. And being able to represent the knowledge of humor is, says, AI complete. Okay, if you can represent knowledge of humor, you can represent anything. Okay. Okay, this is the answer. I forget to answer. So, what are the knowledge representation of event? It's just a Cartesian product of sphere configuration of many kinds. The simplest case, I will not move it, so stop again. It's just a start and end. Each is the sphere configuration. And this configuration is a temporal and spatial. No temporal, just spatial. Where you can using topological distance and orientation is enough for everyday life. We can add a middle, okay, between start and end, the same way of representation. Or we can add a start and then add a temporal duration, how last the event goes. Or we can add an action. Implicitly talk about the event and how the object move. So again, event is nothing new besides this. Just understood as the single object, but it's a 4D entity. So let me summarize today's talk. I start from the sphere neural network to represent syllogistic reasoning. Syllogistic reasoning is represented by set theoretical relation between spheres, Euler diagram. Okay, so inversely, we have knowledge of set theoretic symbolic knowledge. We're using sphere neural network to create a sphere configuration in the embedding space. The relation between traditional neural network is that we're using data. And we represent these data in as a vector embedding and optimize it using traditional neural network. They can be well preserved at the center of the sphere. Okay. And then this means sphere is the generalization from traditional neural network. So by adding a non-zero radius, so it's a form a boundary to represent a set theoretical knowledge. Then the first law is said, I just said, it's the generalization. The second is that using sphere configuration, we can represent common sense knowledge from space, time, and event. And this should be the more fundamental to develop abstract concept like point. The second law of sphere and neural network is more fundamental. And let me say, what's that? The next talk, I will talk about how to reason with sphere neural network in recognizing home, wayfinding, and other way. And this forms the thesis of Herbert Humer's neural thesis. That's the end of my talk. Let me stop recording. Still recording.